Morning, everyone. Um, I am assuming that people are finding it difficult to find a room and come here, or they feel that Athena is a better service. I'm not sure. So, thank you. I'm honored to be introduced by Alexa. Today's session, we are going to talk about some recent features that we released in Redshift, some best practices, right? What you can take away from here. If you're not following these best practices, can you start following these best practices? And also some additional resources. Many of you, if you have spoken to your SAs, account managers, you'd be knowing these additional resources, but these are very critical for you to monitor your Redshift cluster and how to tune your Redshift cluster. So, are you a Redshift user? Raise of hand, please. Okay, I've got one person using Redshift, that's good. So, Redshift is not a database. But what we did is we chose something that is a database, which you are all familiar with, something like PostgreSQL, and we added MPP capabilities into it, OLAP capabilities into it, and columnar capabilities into that database, and added a slew of additional services that are running on AWS, like SWF, like VPCs, like KMS, Route 53, and made it available as a service to you called Amazon Redshift. So it's not a PostgreSQL database. We expose PostgreSQL views for you, but it is not a PostgreSQL database internally. We have introduced 125 significant patches since we launched, and 165 significant features since we launched Redshift. So when a feature is released, you don't have to come to us to say, can you enable that feature for us? The feature is automatically added to your Redshift cluster. It's available in the next patch release. So you don't have to do anything for it to move towards a new patch or a new feature set. Everything is automated for you. Fully managed, fully automated. So, looking at the Redshift architecture, we have a leader node. The leader node is your SQL endpoint, which is where you send your SQL queries to. It's your JDBC, ODBC endpoint as well. It stores metadata about the cluster in itself. It stores details about which node in the cluster is having this particular key space, what are all the queries that have been running on that, what failed queries are there, whether we are using certain parameters like short query acceleration, which I'm going to talk about, and these kind of stuff are stored in the metadata. It also coordinates your SQL processing. It says, which node should execute this piece of the query? It converts your SQL queries into C code and pushes it into the core nodes and then consumes it. Your compute nodes are local store, columnar stores. They are locally storing all your data on local disks. It executes queries in parallel. Each of the nodes also have multiple CPUs in them, so they execute things in parallel. Each CPU is a slice for us. It also helps you to load, unload backup from the compute nodes. The leader node doesn't get involved in this. You may send a request to unload data, or you may send a request to back up your cluster, but all the hard work is being done by the compute nodes. It's not being done by the leader node. Last year, we released Redshift Spectrum, which allows you to go and query data from the S3 buckets without having to load the data into a Redshift cluster. Customers were asking us for this feature for a long time. There are two reasons that you increase the size of a cluster. One reason is you have run out of storage space, so you need to add more storage space, or you want more processing power. We want you to increase the size of the cluster only because you have run out of processing power, not because you run out of storage. We would like you to keep data that is not being frequently queried in the S3 layer and query it from Redshift Spectrum. Redshift Spectrum is a massive cluster that runs. It's a multi-tenant cluster that runs underneath Redshift, and it is accessible only via Redshift. It's not accessible outside Redshift. So, you should be thinking toaster when I say Redshift. So you don't want to know the underlying inside workings of the toaster. What you want to know is, how can I tune my toaster so that my bread comes out in perfection, right? I need to understand what are all the tuners that are available for me, knobs that are available. How can I increase, how can I make it more warmer? How can I, there is a freeze button on the toaster. How do I use that freeze button? All you need to do is that, right? It runs fast and cheap. That's what we want it to do. It just runs. I don't want to worry about, hey, what's happening internally on the toaster. Similarly, Redshift is something like that, and we want it to be a toaster for you. But what we also want you to know is, what are all the knobs available for you to tune your Redshift cluster for peak performance? And I'm going to walk you through a few of them today. And I'm happy to take questions. I'll be available outside after this if you want to dive deep on certain areas, or send me an email as well. The first feature that we released, which we did not market too well, was short query acceleration. A new queue is enabled for queries. A queue is where your queries run on Redshift. So on the queue, we actually run the Redshift, and we give 6 slots in that queue. If you have set up your total concurrent users to be less than 15, then short query acceleration is by default enabled for you. You can enable short query acceleration via the API even if you have set it over 15, but we feel that the ideal number should be 15, or else you are going to unnecessarily load the Redshift cluster. So when a query is executing, based on machine learning algorithms, it understands which query and what time it is going to execute for. And then if it feels that this query is going to execute within 3 seconds or 5 seconds, it takes it out of its original queue and runs it on the new queue that we have created with 6 slots on it. This query, once it finishes, the customer gets the results. He did not have to wait for it. If it doesn't finish, for some reason that's not finish in 5 seconds that we anticipated that it will finish, we will take the query and put it back in the same place in the old queue from where we took it out, which means the user doesn't feel anything. He just continues to wait for the query to complete. Once the query completes, he gets the result out of it. What is the advantage of doing short query acceleration? The advantages of doing short query acceleration is to ensure that people don't wait for queries to complete. We don't wait for queries to complete. So if I can remove 5 queries from the queue, then 5 more queries can run faster on the existing queues. That's the whole idea behind short query acceleration. Based on initial tests that we did, based on the private beta that we opened up for customers, we got a 3x throughput improvement on short query workloads with minimal effect on long-running queries. There's no effect on long-running queries. The short queries started working better. If you are having a queue separate for short queries, you may want to disregard that queue and start using short query acceleration. It's a tick box in the console. The tick box is enabled only if your concurrency is set to less than 15. And it's an API call. The API call can be called even if your concurrency level is over 50. Results caching. This is one of the other features that we launched, which helps you to fast track your query through the queue. We will cache your results for a query that has run, and next time when you run the same query, we will give you the results from the cache and not have to go and fetch all the data and process the query. We are fully ACID compliant, so if you update the record, we will remove the results at cache. So you don't have to worry about getting stale data to your customers. And we will provide you a cache size that is proportional to the node type. So if you choose a node type which is smaller, you get a lesser cache. If you choose a higher, bigger node type, you get a bigger cache for it. We have given you a view that tells you whether the query was returned because from a cached query or from a regular query. Right? Late materialization. This was a feature that we launched, but People really did not understand this, maybe. And this was, again, something that just got switched on, right? It was not something you had to configure, tune, or anything like that. So late materialization is aimed at reducing I/O on columns. When you are reading columns with predicate filters on them, we can actually reduce the amount of I/O that we do on it. With late materialization, you can also have compression on sort keys, because when we read the data, we would be able to understand and apply the predicates before you start using the query to get more data out of the query. A new column called isRLF_scan on STL scan table tells you whether we used late materialization on a particular query, and you can figure out how many late materialization queries I've run and how much of I/O you have saved. And every I/O saved is a query running faster on Redshift. This is something, again, we tuned inside the cluster, not great marketing. We did not do any kind of marketing on this. We increased the commit speeds. When you're running your queries, read-only queries, we have now started to batch all the checkpoints together. And these checkpoint batching effectively means that your queries are running faster, executing faster on temporary tables as well. We will continue to work on this. This is not the end of it. We will continue to work on it. We will continue to work to ensure that we are able to provide better checkpointing on the Redshift cluster. Awesome. So those are the features that I wanted to talk about. Let us now get into the best practices for using a Redshift cluster. Migration. Don't do a lift and shift. Friends, don't let friends do lift and shift of their data warehousing clusters into Redshift. Please make sure that you follow our design guidelines. Make sure that you follow our best practices to bring up your Redshift cluster and port your data from your existing data warehouse into Redshift. Your final solution will use other AWS services as well. It will not only be Redshift. So you may want to glue in certain other services with Redshift. For example, you may want to put a PostgreSQL database having a materialized view of the data from Redshift. You can do that today. So you are not constrained only by Redshift. So think out of the box. See how you can make your data warehouse better. So lifting and shifting doesn't solve your problem. You may end up in more problems when you do lift and shift. Please make use of solutions architects, ProServe, partners to come and help you. Don't wait till the problem has hit the roof. All right? Call us early on. We are happy to work with you. We are happy to work with you to identify the solution for you, identify table designs for you, so that you can get the maximum out of the Redshift cluster. Talk to your account teams. We are more than happy to help you. Data distribution is very important for a MPP data warehouse. We offer you 3 kinds of data distributions. One is key level distribution, where you define a key and we will distribute the data based on the key. The other one is event distribution, where we will evenly distribute the data of a table across the cluster, all the slices in the cluster. The all distribution keeps the data in the first slice of every node. So if a node has 2 slices, the first slice will always have the data. So the data is duplicated. You need to be careful when you use all, because you don't want to use all on a 15 billion row table. You will basically be duplicating the data into all the nodes. Whereas all may be a good distribution style for your date dimension. Your data that is less than a few million rows can be easily distributed on the all style. Right? The whole idea behind distribution is to distribute the data evenly for parallel processing and also reduce the network chatter between the nodes. Any network chatter is I/O, and if I cannot reduce the I/O, my queries are not going to run faster. So I need to reduce my I/O. Again, distribution is very, very critical for your optimal performance of your Redshift cluster. Table design. I always say to customers that 80% of your Redshift cluster performance is table design. 20% is, or 15% is query tuning, and 5% is our toaster, which is Redshift. Everything else is in your hands. If you don't design properly, you will not get the best out of Redshift. Materialize often filtered columns into fact tables. We like star schemas. When I say this, people say, hey, don't you like star schemas? Absolutely, we love star schemas. Right? Redshift loves star schemas. But then, if I'm going to join 300 tables to derive a value for a query, can I materialize that data into my fact table and reduce the number of joins I do? Every join is an I/O. Can I reduce the I/O that I do on a particular Redshift cluster? Having said that, I cannot materialize every dimension into the fact table. I would want to still have dimensions outside, like my type 2 dimensions. I would like to have type 2 dimensions, and these dimensions have to live outside. We are not saying denormalize completely. We are saying denormalize where possible. For example, in your address table, if you have a country table and an address table and a country ID in your address table, you can say, I will move my country codes into the address table. I don't need to have it separately. Right? So try to materialize what you can materialize, leave what you cannot materialize, and we will work through that. Keep data types as wide as necessary. I've seen customers go and say, I'm just going to say varchar 256 for everything. That's not a good practice, because I need to allocate 256 bytes of memory when I want to process that data. And when you say, and you're only going to store like 5 characters in it, why do you want to allocate 256 bytes of memory on it? Right? So we would like you to be cautious and conscious of the fact that you would want to only allocate the amount of memory that is needed, so that your load operations are faster, your queries run faster as well. Compression to columns, very critical. Please add compression to columns. You need compression. Compression, we do anywhere from 2x to 4x compression on Redshift, on data stored in Redshift. And when you compress your data, the amount of I/O we do is limited as well. So please do compression, which will improve your query performance. Add sort keys. Don't run without sort keys. You already know where you're filtering on. Whenever you're filtering on, use those filter columns as your sort keys. That will improve your query performance, dramatically improve your query performance. So coming to copy and unload, we recommend delimited files. Don't do fixed width files. Prefer delimited files. Fixed width files, the processor has to do more job to identify the data. Delimited files are better. Every slice in a Redshift cluster, if you run a DC to X large, we have 2 slices in every node. So every slice in the Redshift cluster can actually load data. So instead of giving us one massive 5 terabyte file, and you have a 10 node cluster of DC to X large, which basically means you have 20 slices, split the file into 20 chunks and give it to us. And the load process will be way faster when you do that. Right? Files should be 1 MB to 1 gig after compression. Don't give us files more than that, because we cannot really process them fast. So if you split your files and give it to us, that's the best way to do it. And split it at 1 gig chunks. Use unload to extract large amounts of data. You can still use select statements to extract the data, but then the select statements are all funneled through the leader node. Whereas when you use an unload function to extract the data, the unload function actually operates on the data nodes or the compute nodes, and they run way faster in parallel as well. You can run non-parallel unloads. Why do you want to run non-parallel unloads? An unload operation will generate multiple files, a file per slice that you are having. If you want to get a single file, then it makes sense to run a non-parallel unload, but do it only for small amounts of data, or else you will be hogging the system trying to extract all that data through a single node. Okay. There are customers who do ETLs, extract, transform, load, and there are customers who do ELTs, extract, load, and then do a transform. And that's a good practice. It's not something that we say you should not do. We just say that be aware of these best practices when you do an ELT. A ELT is done by customers because they feel they have a Redshift cluster that's not doing any work overnight. And why would I spin up another EMR cluster or a glue cluster to do the transformation? Why can't I do the transformations on Redshift, on SQL? So when you're doing transformations, use temporary tables with backup no option. We don't want to back up your temporary tables, your staging tables, your load tables. We don't want to back them up. Put a backup no option to them so that backups are not triggered for the huge amount of data that you're bringing in for you to do transformations on. Use the same style of distribution between the staging tables and the primary tables so that insert into selects are way faster. They are not hindered by distribution. If you're copying a lot of data, use alter table append instead of insert as select. Alter table append, what it will do is it will take all the blocks of data, format the blocks, and attach it to the existing table. That's way faster than using insert as select. Don't do compression settings on comp update off. Put comp update off so that default compressions are not done. Use analyze compression and do the compression on those staging tables, or copy the compression from your target tables into the staging tables. This is like brushing your teeth. You need to do it daily. No options. Right? If you don't do it, you're going to have problems later on. Sure, for sure, right? So vacuum and analyze are critical things. Vacuum, do it daily, at least a delete-only vacuum daily so that your rows which are deleted are compacted and kept. And do a vacuum weekly which runs on a full table, resorts the table, compresses the data, gives you a very clean table with no empty blocks in them. Analyze can be run periodically after ingestion so that the optimizer gets the statistics of your ingestion. Analyze is meant for the optimizer. It's meant for the optimizer to decide whether I should do a merge join, whether I should do a nested loop, whether I should do a hash join. There is a utility to vacuum and analyze all the tables in the cluster. You can use that utility. It's available on GitHub, on the AWS Labs section. Please feel free to go and download it, modify it. We have customers who have done changes to these scripts and given it back to us and improved the quality of these scripts. Workload management and query monitoring rules. Workload management allows you to specify queues and allows you to kill your queries if they are running over time, if they don't have enough memory, enough CPU usage on them. QMR goes the other way around. It says, let me monitor your query and tell you whether you are going to exceed the quota given to you, and then I will go and kill the query. Use QMR to better manage your queries than WLM. WLM should be used as the queuing technology for your business users, for your general managers, for your data analysts, separate queues for each of them. But then QMR can be used for fine-grained access to those, saying, hey, if a business analyst runs a query and it runs for more than 10 minutes, kill the query, right? And again, don't start off by killing the queries. You don't want to kill a query of your GM, right? Because he ran a query for 10 minutes or more. Start logging these queries. Look at the queries, look at the logs, and then understand what queries are running, and then decide what needs to be killed, what are the functions that you need to use to kill it, or whether you need to, it may not be the number of records, right? It may be the amount of GB that he is fetching from Spectrum. You may want to use QMR to even monitor and kill those queries. Save the super user queue for administrative tasks only. Don't give it off to your data analyst and ask them to run queries on that. That is meant for administrative tasks. If that queue is also blocked, you don't have no ways of getting into the cluster to run a query, to kill a query, or to make modifications to a long-running query, right? Please make sure you use that. We recommend that you use QMR for timeouts and not WLM. They both do the same kind of things, but they come from different angles, and it is easier to work with QMR to manage this whole thing. Cluster sizing. Again, I have seen customers come and tell me, hey, I'm going to run a single node cluster. Don't do that for production. It's good for test, but don't do that for production. When you run a single node cluster, we run the leader node inside that single node cluster. So the amount of CPU cycles required to run the leader node is consumed from that single node that you are having. If you run more than 2 nodes, we will give you a leader node outside your data nodes or your compute nodes, which effectively means your leader node is free of charge. We don't charge you for your leader node. So please run more than 1 node Redshift clusters. Testing purpose, single node Redshift clusters are good. The other challenge with single node clusters or small node clusters is every Spectrum job is allocated 10 nodes per slice, right? Or thereabouts. So when there are only 10 nodes that are allocated, you will only get so much processing power from Spectrum. So you will not be able to go and fetch petabytes of data from Spectrum by running a single Redshift cluster node, right? So what we want you to do is size your cluster appropriately and use Spectrum for all the data that is being life-cycled to S3 from the Redshift cluster. It's not used for, hey, I'll use Spectrum as an access layer for my data. It's not supposed to be used like that. It's supposed to be used like your lifecycle data is sitting in S3, which is over 7 years old, and 5 years worth of data is sitting on the Redshift cluster. I want to join these two, then I would use Redshift for that. I'll use Spectrum for that. Maintain at least 20% free space. Remember, we are compressing the data. When we want to do some work on the data, we need to uncompress the data. We need that space to uncompress and run your queries. We need to uncompress and do update statements, delete statements. We need data for doing all that. So please have 20% free space in your cluster for doing that. So again, just repeating that point, there, maximum number of available Spectrum nodes is a function of your Redshift cluster size. Remember that always. If you're using DC1 instances, anybody using DC1s yet today here? Okay. DC1 is our old generation instance, compute instances. Please move to DC2 instances. DC2 instances are far better, same price, no additional price you have to pay. If you've got reserved instances, please talk to your account teams. We are more than happy to migrate your reserved instances from DC1s to DC2s. Right? So, a few additional resources before I close this talk. Labs on GitHub. We have admin scripts, which allow you to do administrative tasks on the Redshift cluster. We have admin views. We have the Analyse and Vacuum utility that I spoke about. So you can do Analyse and Vacuum for all the tables in the Redshift cluster. It's a column encoding utility, which allows you to look at what are the encoding types suitable for your table, drops the table, recreates the table, and copies the data back in. So it's a one-stop shop for improving your encoding for your tables. You don't have to do it regularly, but at least try to do it yearly once, because your data patterns would have changed from the day you started. We would have introduced newer encoding algorithms, and that should help you to run your Redshift cluster optimal. So these 3 blogs, the first one, table design playbook. Please take a printout of it and keep it on your desk. Anytime you are doing design, data model design, please refer to this. Very critical, highly recommended. Top 10 performance tuning techniques for Amazon Redshift. It covers a lot of what I spoke today, but in more depth. Please refer to this blog as well. If you are using Spectrum, I would recommend that you see these 10 best practices for using Redshift Spectrum. And remember, Redshift Spectrum is not Athena. They are 2 different services, right? So please, when something doesn't work in Spectrum, don't say, hey, it works in Athena, why is it not working in Spectrum? They are 2 different services. And we are trying to make it as close to each other as possible. Feel free to give us your comments on what you think is working, what is not working, and we are happy to improve on it. So back to our toaster. Redshift is the toaster for you. We want you to think of it as a toaster. We are working towards making it the toaster so that you don't have to worry about any of those knobs. But you still need those buttons and knobs to get the optimal use of the toaster, and you need to use that in Redshift as well. Good data modeling, good distribution keys, good encoding, sort keys, cluster size, all these form important parts of your Redshift design. I hope you enjoyed this talk today. Please fill in your feedbacks, very important for us, so that we can improve this session for the next summit. Let me know if you have any questions. I don't think I have time to take questions here, but I'm available outside if you want to ask any questions. Thank you, guys. Cheers.